Hello, my name is Fionn and I'm going to talk to you about the largest connected subgraph game. This is joint work with Julien, Bensmail, Foivos, Fioravantes, and Nicolas. First, I'll talk to you about connection games, which are games in which the players strive to make connected structures. For example, the game of Hex, which is very famous. In the game of Hex, there's Alice versus Bob. Alice owns the red sides of the board, and Bob owns the blue sides. And in each round, Alice first colors an uncolored tile red, as such, and then Bob colors one blue. And the winner is the player whose sides of the board are connected by their tiles at the end. So successive rounds take place. Alice, then Bob at each round. And eventually, one of the players manages to connect both their sides of the board. In this case, it was Alice, and so she wins. There are also other connection games, such as the Shannon switching game and Havana. Another class of games are scoring games, which are the ones in which the player at the highest score wins. These were first studied in the 1950s by Milner and Hanner, but only recently was a general framework developed by Larson et al. One of the most famous of these games is the graph grabbing game. So Alice and Bob play on a weighted graph, and each round, first Alice removes a non-cut vertex and scores its weight. So here Alice removes the vertex of weight 2 and scores 2, and then Bob can do the same. He removes the vertex of weight 6 and scores 6. And the winner is the player at the highest score when no vertices are left. So here, Alice can't remove the vertex of weight 5 because it's a cut vertex, so she removes the one of weight 3. Similarly, Bob takes the one of weight 2, but now Alice can take the one of weight 5, and Bob is forced to take the last one, so Bob loses 10-9. Other examples of scoring games include the orthogonal coloring game and influence. Now I can introduce the game of this paper, which is the largest connected subgraph game, which is both a connection game and a scoring game on graphs. So it's Alice versus Bob on a graph. Initially, no vertex is colored, and in each round, first Alice colors an uncolored vertex red, and then Bob colors one blue. And the winner is the player at the largest connected subgraph of their color, and a largest in terms of the number of vertices. And this is when the game ends, so when all the vertices are colored. So Alice plays again, Bob plays again. They keep alternating, and finally in the last turn, Bob must color this vertex. And we can see that there's a connected red subgraph of order 4, but the largest connected blue subgraph is of order 3, and so Alice wins 4-3. To have another example, in this graph, Bob will always play symmetric to Alice's play. And so what we'll see in the end is that they will get a draw. And so in this case, the largest connected red subgraph is of order 3, and the largest connected blue subgraph is of order 3. And so it ends in a draw 3-3. So the results I'll talk about in this talk are the preliminary results first. So showing that Alice always has a strategy that ensures Bob never wins. And so Bob can hope at best for a draw. Then I'll discuss about reflection graphs, which are a large class of graphs where Bob can force a draw. Then in terms of complexity, I'll talk about how recognizing reflection graphs is GI hard. And more interestingly, that determining the outcome of the game is p-space complete. And then since the game is already p-space complete, we'll focus on graph classes, such as paths, cycles, and cographs. And what we'll see is that paths and cycles, Alice and Bob employ a certain type of strategy because they are sparse graphs in terms of their number of edges, while cographs can also be very dense graphs, and so they require Alice and Bob to have different strategies at times, in particular, trying to maximize the size of one single connected component. So first, let's talk about how Bob never wins. So it's so-called strategy stealing. So let's have a proof by contradiction. Let's assume that S is a winning strategy for Bob and G. What Alice will do is she'll cover any vertex in G, any arbitrary vertex, and then she'll follow S as a second player. Now, at some point, while she's following S, she may be asked to color a vertex that is already colored. But in this case, it must be red because she's the one that had the extra turn at the beginning. And so in this case, Alice colors any other vertex and then resumes her strategy S again. And at the end of the game, what we have is that Alice covered all the vertices by S, at least all these vertices. And since S is winning for the second player, then Alice must win. But this is a contradiction because S was a winning strategy for Bob. And so at best, Bob can always hope for a draw. But actually, there's a large class of graphs called reflection graphs where Bob can ensure that there's a draw. So a reflection graph is just a graph in which its vertex set can be partitioned into two sets of the same size, U and V, such that there's an isomorphism between GU, so the subgraph induced by the vertices of U, and GV. And if we set this isomorphism, this mapping, such that the image of UI is always VI for all I, then for the second condition, we need that for any two I and J and one to N. If UI Vj is an edge, then the edge Uj Vi also exists. So essentially, we see in the drawing on the right, here we have a reflection graph. And the second condition is just saying that the edges between the two copies of the graph must be symmetric to each other. So for example, the edge U3 to V5 exists, so the edge U5 to V3 must also exist. But then we can also have edges like U4 to V4 and non-edges like U2 to V2. And it's not too hard to see that Bob can enforce a draw on this kind of graph, because whenever Alice covers a vertex UI, then Bob covers VI, and vice versa. So Bob is always covering the image of the vertex Alice covered. And so for any red subgraph at the end, any connected red subgraph, there's an isomorphic copy that's a blue subgraph. Furthermore, we can actually show that recognizing reflection graphs is GI hard, which essentially means it's as hard as the graph isomorphism problem, which is believed to be somewhere in between P and NP in its own class of graph complexity. So now we'll move on to studying the complexity of the game in general. We can show that it's p-space complete to decide the outcome of the game, and even in bipartite graphs of small diameter. So reduction is from a two-player game called post-CNF, one of the most famous p-space hard problems. So the input is a set of variables x, a CNF formula phi, that consists of variables from x in their positive form only. And each round, Alice sets a variable that is not yet set to true, and then Bob sets one to false. Once all the variables have been assigned true values, Alice wins if phi is true, and Bob wins if phi is false. So how we construct our graph from an instance of phi? Well, for each variable, we take a variable vertex xi. So these are the x1 to xn. And for each clause, we make 6 copies of it. So 6 vertices. And then we have the usual adjacencies. So whenever a variable appears in a clause, then that variable vertex is adjacent to all 6 copies of that clause. Then we have a vertex u that's universal to all the variable vertices. And the rest of the graph is self-explanatory with the picture. Now, if you want to show the first direction, so Alice wins in post-CNF and phi, then Alice wins the largest connected subgraph game in G. What we'll first do is Alice will employ a pairing strategy for the clauses such that she will always, whenever Bob covers a copy of a clause, Alice covers another copy of the same clause. And so she'll get half of each of the copies of each of the clauses. And so essentially, these we can already assume are colored, and Alice will cover U on her first turn. Now there are 2 cases, whether Bob covers a vertex in the top or whether he covers a vertex in the bottom. If he covers a vertex in the top, then we can assume that it's on the left side, for example, or in the middle. And so V2 and W2 are open, and so Alice covers V2. And now Bob must cover W2, because otherwise Alice will cover W2, and she will dominate all the Y vertices and all the X vertices. Well, Bob will never be able to do so because U is a cut vertex separating these. And so this will be enough for Alice to win. So Bob must have covered W2. And now Alice covers X2, which essentially she covers a variable vertex according to our winning strategy in phi, which in this example we say is X2. And now whenever Bob covers a vertex in the top part, Alice also covers one in the top part. Whenever Bob covers one in the bottom part, Alice covers one in the bottom part following her winning strategy in post-CNF and phi. And so what you'll see here on the right is that both players have the same score essentially, except that Alice has half of the variable vertices rounded up, while Bob has half of them rounded down. And so we actually need that the post-CNF instance has an odd number of variables. And this, of course, still remains p-space hard. So this we can assume. The second case is that Bob colored a variable vertex at the bottom. And in this case, Alice colors W2, which again, as before, forces Bob to color V2. And then she colors W1, which forces Bob to color V1. And now she colors one of the Y vertices, let's say Y1. And she will construct her largest connected subgraph in the top part, while Bob will have to construct his largest connected subgraph in the bottom part. And again, we'll have that Alice wins, but just by one again. In the other direction, if Bob wins in post-CNF and phi, he will also employ a pairing strategy for the clauses. And then whenever Alice plays a variable vertex, he will play according to post-CNF and phi on the variable vertices. So we can assume these are already colored. And now we have to take multiple cases, but let's just assume Alice colors U. The idea for Bob is to color W2. We can always ensure that one of W1 or W2 is not colored. So let's say he colors W2, and then from there, he will just ensure that Alice never connects the top part to the bottom part in terms of the Y's to the X's. And they will both have the largest connected subgraph in the top part, because even though Alice is playing on the variable vertices first, Bob has a winning strategy in phi, and so there's at least one clause that will not see any red vertices in the variable vertices, and so Alice will not get three vertices in her connected subgraph in the bottom because of this. And that difference of 3 is enough to make it that she doesn't win in the bottom, and so they both construct their largest connected subgraphs in the top part. So now, since the problem is already p-space complete in bipartite graphs, we look at some simpler graph classes. So for example, paths. In the path, Alice wins if and only if the number of vertices is an odd number between 1 and 9. So for the smaller cases, it's just a case analysis. Alice always covers the middle, and then Bob has to cover one side. And for example, here, once Alice covers this vertex, it's clear that she wins. For 7 vertices, there are multiple cases, but if we just take this case, then Alice will cover V6, forcing Bob to cover V5, as otherwise she will get its correct component size 3. And then Alice covers V2, and clearly she wins again. When n is even, what you can notice is that the path is a reflection graph, and so Bob can force a draw. So the only case left to do is to show that Bob can force a draw when n is at least 11 and n is odd. So we have multiple lemmas to be able to prove this. So the first one says that even if there's initially one of the ends of the path is red and Alice plays first, then Bob can still ensure that any connected red subgraph has order at most 2. So the idea is that when Alice covers Vj, Bob will cover Vj minus 1 if he's able to. And if he's not able to, then he'll cover Vj plus 1. And otherwise, he covers any arbitrary vertex. And to see that it's true, well, let's suppose in search of a contradiction that Alice is able to cover 3 red vertices in a row, Vj minus 1 through Vj plus 1. And what you have to notice is that Alice must have covered them in that order, because otherwise Bob would have covered the one to the left of it. And so he would have stopped them being 3 in a row. So when Alice covers Vj minus 1, let's say Bob covers Vj minus 2, and the contradiction happens when Alice tries to cover Vj, because now Bob must cover Vj plus 1. The second lemma says that if there are x vertices that are initially red, and they include one of the ends of the path, and Bob plays first, then Bob can ensure that any connected red subgraph has order at most x. So here we have an example for x equal to 3. Bob covers this vertex. And so now, according to lemma 1, on the left, Alice can never score more than 2. Another configuration that was possible for x equal to 3 is this. Bob covers this vertex. On the right, by lemma 1, he's good. On the left, by lemma 1, Alice scores at most 2. And then if you add that last vertex, then it's at most 3. So still at most x. So this lemma actually implies a third lemma, which says that if there are x degree 2 vertices of Pn that are initially red and Bob plays first, then Bob can stop any connected red subgraph of order more than x plus 1. And so the idea is just then to take the general case for paths with n, at least n greater than or equal to 11 vertices. And what you can see is that because of the size of the path, there are at least 5 vertices without loss of general weight to the left of the first vertex Alice colors. So for example, to the left of V8. And what Bob does is he covers V7, which forces on the right that lemma 1, by lemma 1, Alice scores at most 2. And now there are 2 choices for Alice. Either she covers V6 or some vertex to the left of V6. If she covers some vertex to the left of V6, like V4, then what Bob does is he covers V6, and now he uses lemma 3 on the left side to make sure that Alice scores almost 2, and so they have a draw. And otherwise, Alice covers V6, and Bob covers V4. And now if Alice covers V5, well, then Bob can cover V3 and get his draw. And so Alice must cover vertex to the left of V4, for example, V2. Now Bob covers V5, and by lemma 3 again, he gets a draw. And so note that we needed 5 vertices to the left because when Alice covered V6 and Bob covered V4, he needed that V3 existed in order to stop Alice from covering V5. So in general, for paths, we have the result. And then for cycles, we can, again, do similar results. So in cycles, we show that Alice wins if and only if n is odd. So when n is even, again, it's a reflection graph, so Bob can force a draw. So we need to show that Alice wins when n is odd. And so first we have this lemma that says if x vertices of a path Pn, or including its ends, are initially blue and Alice plays first, then Alice can assure any connected blue subgraph has order at most x minus 1. And so the idea is that if Alice can force a situation like this in the cycle, then she'll win. So essentially she makes one connected component after x turns. So V1 through Vx. And if Bob has covered the other 2 ends of the path that's separating Alice's path from the rest of the cycle, so Vn and Vx plus 1, then essentially he's playing on a path where he's covered both ends and he's covered at most x vertices inside this path. And so Alice can apply the lemma on the rest of the graph and ensure that Bob has a connected blue subgraph of order at most x minus 1, while she already has one of order x. So if she can force the situation to happen, then she wins. So how does she force the situation to happen? Initially, she covers some vertex, and Bob covers some vertex. Here we'll say it's Vn. And then she covers 1, 2 vertices away. So now if Bob doesn't cover V2, then Alice covers V2 and then keeps building her single connected component until Bob stops it, in which case we arrive at the situation before. So Bob must cover V2. Then she covers V5, Bob must cover V4 for the same reasons. And she continues this all the way to the end of the cycle. And what we get is that because n is odd, at some point there must be 2 consecutive red vertices. So Vn minus 1, Vn minus 2. And so Alice will win with a score of 2 to 1. So now we move to last class of graphs we'll look at, which are cographs, which are also known as P4 free graphs. So they can be defined recursively as follows. A single vertex is a cograph. And if G1 and G2 are 2 cographs, then the disjoint union is also a cograph. And the join is a cograph, which we call a join cograph. So the join is just you take the 2 cographs and you put all the edges possible between them. And what we have is that we can determine the outcome of the game in the cograph in linear time. So the usual idea for problems in cographs is to consider 2 cases. So the disjoint union and the join. So the first case is easy. The case of a join is easy. But the case of a disjoint union is difficult because essentially we don't know how the game works when a player can play successive turns in the same connected component. So maybe the Alice plays in one component and Bob plays in the other. And so now Alice can play again in the same component. So 2 turns in a row. And this makes it very difficult to compute the outcome of the game for disjoint unions of graphs in general. So the solution we have is that we take the decomposition of G into a disjoint union of cographs that are all joins. So here we have a decomposition of G. decompositions of cographs can be found in linear time. And if you look closely at the figure, what you'll see is that equivalently, we can say that, so G is equal to the disjoint unit of G1 plus G2, but we have that G1 is not a joint cograph. So equivalently, you can actually see that G is equal to the disjoint unit of G2, G3, and G4, where all of these are joint cographs. And so we can get an equivalent definition where we say that G is either the join between two cographs or the disjoint union of multiple joint cographs. From there, we can deal with the cases separately. So if G is just a join between two cographs, then let's define A star to be the class of graphs in which Alice can ensure a single connected red component. So class of graphs where Alice can ensure a connected red component of order at least half the vertices, so half the vertices rounded up. And the simple observation to make is that if G is a join of two cographs, then G must be an A star, so Alice can make one connected red component. And if both these cographs have at least two vertices, then Bob can ensure a connected blue subgraph of at least half the vertices rounded down. So the idea is just simply like Alice covers on one of the graphs, Bob covers on the same cograph. Whenever Alice covers on the other one, Bob covers on the other one, and now they both dominate all the vertices of G, and so they both can get half their vertices. Alice rounded up, Bob rounded down. And then in particular cases, when one of the cographs has only one vertex, in which case it becomes more difficult to see what Bob can do, since Alice can cover that vertex first. And so in this case, Bob can only ensure a connected blue subgraph of the order of half the vertices of G if the second cograph is in A star. So now we deal with the other case where G is the disjoint union of multiple joint cographs. And what we do is that we would sort them in decreasing order in terms of number of vertices. And then the outcome of the game actually only depends on the biggest one, so the three biggest ones in terms of number of vertices. And to see why this is true is simply that Alice and Bob can both employ pairing strategies on the smaller ones. And since Alice can always score at least half the vertices in any of the cographs, well, these are of no consequence in the big scheme of things. So essentially you can just get rid of them and look at the biggest cographs, the three biggest ones in particular. Then the sketch of the proof is just to do an induction on the number of vertices, with the inductive hypothesis to be that you can determine the outcome in any of the GI and whether or not the GI is an A star in linear time. And then this is a tedious case analysis for the three biggest cographs. And you do the cases based on whether or not each of them is a join of a singleton, the parity of the number of vertices in each of these cographs, and whether or not they are an A star or not. So interesting for the work would be to look at other graph classes such as trees, interval graphs, and grids of odd order. So we know for grids of even order, they are reflection graphs. So we know that Bob can force a draw. So it'd be interesting to know what happens in grids of odd order. It would be interesting to understand in a broader scheme how this game works. So this would be looking for like necessary and sufficient conditions for a graph to be an A star. So again, graphs in which Alice can force that she gets at least half the vertices rounded up. And in a similar flavor, it would be interesting to look at a make or breaker variant of this game in its own interest, but also towards understanding better the previous game, the original game. So in this variant, it would be in each round, Alice covers an uncolored vertex red, and then Bob deletes an uncolored vertex. And the question is, what's the maximum order of a connected red subgraph in this setting? And so essentially, this is quite important because in some graphs in the original game, Bob doesn't have any interest in making a big connected blue subgraph. He just wants to make sure Alice doesn't make a big connected red subgraph. And so if we understood the make or breaker variant, then we'd understand better the make or maker variant, the original game. And that's it. Thank you for watching.